All right, this is again just another very complicated way of saying this is not Washington, meaning that this is a water balance, a real, honest-to-goodness, closed water balance done at the Walnut Gulch Experimental Watershed, run by Department of Agriculture down by Tombstone. 12 inches of water going into Walnut Gulch, 10 of it leaves through evapotranspiration, okay? An arid climate. Again, that gets tipped towards surplus, but only at the highest, wettest parts of the state. And that's not very much of the land area of Arizona, right? We get a lot of water in Arizona from way north of the Arizona border, right? Up in the upper basins of Colorado, where you have much, much higher, much, much cooler climates that can generate snow and snow melt. Okay, so then now I'm gonna back you up and take a look at precip over a 1,000-year time period here. And this has been generated through paleoclimate tree ring reconstructions done down at the Laboratory of Tree Ring Research at University of Arizona. And this is specifically for connecting the instrumental data collected in Yavapai County with tree ring data collected across the region. And what you're able to do then is produce a wintertime, November through April, percent of average or time series graph from about 1080 to about, this I think map goes to 2000, I think it stops short of, it goes to 1988 is the actual value that it stops at here. And so what this means is that the 100% line means that meets the long-term average. So if you took every data point on this graph and you come up with one number, the mean, that's what this line is right here. So then any given year, if it's above this line, means it's above the long-term average, and any line below this means it's below the long-term average. So then we've got, hopefully what you can see from this graph, you don't have to squint your eyes too much, is that we have a lot of interannual variability, right? We swing wildly from very wet to very dry. We have runs of wet years, runs of dry years, and you may even be able to squint your eyes and notice that we have a skewed distribution, meaning that we spend a way more time below average than we do above, because that means we have these extreme events that occasionally occur that are very wet but make our distribution slightly skewed. That just means that, again, we have a background arid climate, and dry conditions are actually the norm here. And I also sort of draw your attention here too that there have been some really, really extensive and deep multi-year droughts in the past. And this is the contemporary record right here, which is we had a pretty deep drought across much of the west, southwest in particular, in the late 1800s. A big jump in the early 1900s towards a wet. This is the 50s drought, and this is that real rapid increase in precipitation peaking in the mid-80s here across Arizona, and this is particularly across Yavapai County. So the variability even in the last 100 years is pretty remarkable given the last 1,000, but I also sort of draw your attention to here is that this, I think, is a reference point for many people in Arizona, is this peak right here. I think a lot of people who've been here for a while think of this as the wet, and again, it's not people who've multi-generational, I think a lot of us who've moved here over time have some expectation for wetter conditions than are actually really here in Arizona. And the wet period of the 80s is always held up as, it was a great time in Arizona, except for flooding and loss of bridges and those kinds of things. Lots of recharge, lots of water, lots of back-to-back. We had seasons where it would rain a lot in the fall, it would rain a lot in the winter, it'd rain a lot in the spring, it'd rain a lot in the summer, then it would rain a lot the next fall, then it would rain a lot the next winter. And again, this is not happening very often in the last 1,000 years, right? That's kind of the point of this graph. Okay, so then let's zoom in here. This is from 1930, again, for Yavapai County. Trying to point that out is that this is the mean line right here. So this means that if you don't see a bar here for a given year, this one's like kind of a good example. This is very close to the average for that year. A bar sticking down means it's below average for that year, and a bar sticking up means it's above average. Well, just look at that. If you count up the number of bars below and above, we actually have more below. And again, this is a little artifact of having a distribution that has more more small events, more below average events, more low events than we do high events. But it also indicates here that we cyclically move from dry conditions interspersed with occasional wet periods. We can have very wet conditions for a month or two or a season in a dry spell, but they're often clustered in runs of below average conditions. here's the wet conditions that have come here in the 80s, cycling back down into drought conditions really since about 1996. Okay, cyclical variability, and for all intents and purposes, this is very strongly related to El Nino Southern Oscillation, cycling between El Nino and La Nina conditions in the Pacific Ocean, which you probably have heard about. We've actually had 2 La Nina winters in a row, which are cooler than average conditions in the Pacific Ocean, which may sound a little bit weird. Why are we talking about the Pacific Ocean? Well, what it does is it impacts the jet stream across the western United States, and it actually moves the storms away from Arizona, in a very simplistic explanation of that. So when you have lots of La Nina winters in a row, you have dry winters in a row, all right? And the Pacific is sloshing back and forth between El Nino and La Nina events here. So in the 50s, we had lots of La Nina events. In the 80s, we had more El Nino events than La Ninas, and we've really slid back here towards having more La Nina events. So we're getting what we call decadal variability, decades kind of behaving similarly as far as precipitation variability, cyclical. Okay. Okay, so this is another graphic to sort of tie it back to stream flows, and you can see here that I'm trying to, the illustration of dry conditions over runs of time. This is the 40s through the 50s and 60s, interspersed with wet conditions, and here's those wet conditions from the 80s on, and then sort of a move here. The stream flows are long-term aggregators. They're great integrators of short-term climate variability because they respond very slowly to this type of climate variability. And then this is another kind of mind-blowing graph that I found on the USGS website. It's brand new. But this graph is, it's the average daily stream flow at the Verde River below Tangle Creek, above Horseshoe Dam, for every day of the year in this direction, for every year from, this is before 1950 through 2010. So what it does is it tells you very low numbers to very high. So you can see these are little blue dots are flooding events. This is the seasonality of flow. And you can also see here, this is dry conditions, even sort of not so dry conditions even through the summertime. So we're looking at the summertime, and then dry conditions. So you can see that decadal variability both through the annual cycle and then over time, through time here. It's a little bit hard graph. You're probably not used to. I'm not even used to looking at this particular one. But I like this showing this sort of widening of the dry period of the spring through summer. It goes away a little bit, and then it comes back again with the most recent drought conditions really coming in and hanging in here. And then you have these episodic. This was 2004, 04, 05, and you look right here. It swamps the annual signal. Again, high climate variability from events at that point. Okay, I'm gonna skip over that. That was the ENSO. Okay, another mind-blowing graph. And try to walk you through this. Okay, so what this graph is trying to communicate here is that this is for Yavapai County again. This is monthly data from 1900 to 2010. So above this line means wet conditions. Below this line, these little bars sticking down mean low average dry conditions. And what this is it's a drought index at short time scales to long time scales. So you get really high variability from month to month. The green indicates wet conditions. The yellow-brown indicate dry conditions. And as you go up this graph, it's integrating and smoothing out long-term drought conditions. So if you look across the graph down here, you're looking at very, very sharp switches from wet to dry, wet to dry, wet to dry, wet to dry. But if you look up here, this is a length of months, so this is 60 months, so this is a 5-year smoothed average. You can see the real long-term drought signal. This is an extended period of dry conditions, wet, dry to normal to dry, dry, wet, 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 and now to dry again. Okay, and I'm just going to zoom in on, and we'll actually point out here, this is the 50s drought. This is that wet period in the early 1900s. This is the 80s drought. Also to point out, the 80s drought, look how wet it was for the whole last 100 years. Very, very wet. Let's just zoom in the last 25, 35 years here. So this is from 1980, same graph. But just to put this in context here is that, again, look at this graph here. We now are really looking for runs of below average conditions are what create short-term drought conditions that turn into long-term drought conditions. So here's the 80s wet period. You know, we've got droughts popping up in the middle of the 80s, but overall, there's enough water, enough of those wet events that it's sort of driving the overall driving the overall drought condition, the overall lack of drought conditions up in longer time scales. So we get to 85 to 90, we start to really get into a run here of average conditions. Believe it or not, we're almost hitting the average every month. And we get here, we start to get a run. This is the drought of 88, 89. Okay, and we start to see this was a pretty extended period of many months in a row driving drought conditions. So it starts to really smear out into longer time scales. Okay, and then here is 92, 93. So we had some epic flooding across a lot of Arizona. And it was enough of events across seasons that it turned into a nice wet signal that went right into longer term conditions and got rid of long-term drought conditions. Okay, so since 1996, we started to get these runs of below average conditions that have set up. And you can look here, since 1996, we've had episodic wet periods, even this one, this is 0405, but it wasn't enough to combat the runs of below average conditions we've had since then. So this is how you get this. It's a little bit dissonant situation, but it rained, but how come drought hasn't gone away? It's because it's this combination of, it can't rain for 1 month or one season above average, right? If you've accumulated many, many months of below average conditions to get rid of drought. This right here, to get rid of drought at this time scale, you need runs of wet period that extend for many, many months, if not years, to get rid of long-term drought. So these episodic wet periods are good for growing things, especially growing grass and helping vegetation out, helping some really ephemeral streams. But this overall is an impact on water resources in the longer term drought conditions. So that's why drought doesn't go away with just one event, I guess was the long way of trying to illustrate that. Okay, great. And again, the gorilla in the room is that if you think about what I talked about earlier, cyclical variability in precipitation, normal natural variability, decadal drought, driven by Pacific variability, we're going to swing into long-term drought. We'll occasionally get these wet periods driven by Pacific and jet stream storm tracks and those kinds of things, but temperatures are on the rise, and the temperatures have deviated from that cyclical variability that's driving precipitation. They're disconnected, okay? And so you see a little bit of this variability in the record here. This is Yavapai. We have lots of swinging back and forth with variability. A warm period here in the 50s and 60s, a cool period in the 70s that really was across the whole globe. And then we've had this real strong rise in temperature and a little bit of a dip as of recent, but overall a consecutive run of above average months that's gone on for 20 years or so. And this is a local record. This is not the global plot of temperature, which I'll show you in a couple of slides, but very consistent with what I'll show you in a couple of slides. So thinking this logic through, we slide into drought periods, we slide into wet periods, but we have this thing with aridity, we have this thing with potential evapotranspiration. And again, remember, warmer conditions drive higher amounts of evapotranspiration. So even under the same amount of precipitation, there's more of an atmospheric demand for the water that comes out of precipitation. So you can drive aridity through warming temperatures alone, which is the big concern. Again, it's much more complicated than that when water gets into soil or mountain front recharge and those kinds of things. I think that this has its greatest bearing on the very simple relationship between vegetation and water. When warming temperatures, that's where we're starting to see the impacts already on killing trees in particular. Okay, so moving now into, that's your climatic context. You're all physical geographers, physical climatologists for Arizona now. Now we're going to do a whole semester in climate science in the next, let's go for 12 minutes to try to do that. And again, this is not necessarily my research, right? I am presenting synthesis work from key resources that are continuing to be pulled together by the Intergovernmental Panel on Climate Change, and probably more importantly for this particular presentation, the U.S. Global Change Research Program, which is a volunteer effort of scientists of all the institutions, including U of A, to assemble climate research into synthesis reports. And there's a report that came out in 2009 of the state of the climate science and particularly the impacts across the U.S., which I'll show you. But there's another report that's actually going to be out next spring that will continue to update this information with very, very regionalized, detailed information on Arizona. It's called the National Climate Assessment going on right now. And there'll be a Southwest chapter that's actually being under review right now, which you're actually, I think, have the ability to go online and actually comment on as part of the federal review process. Okay, so that's the resources I'm presenting, but I'm going to step back. I'm going to go to 7th grade earth science and talk about the greenhouse effect, because this is really the fundamental. You build from this fundamental point of the physics and thermodynamics of the atmosphere, a fundamental mechanism that keeps the Earth's temperature at a temperature that has most of the Earth's water as water, which is really, really good for us. If we had a frozen planet, it's tough to make a go of it here. If the planet is 450 degrees Celsius, not good, right? Not good. So this greenhouse effect is actually a really critical part of maintaining a planetary radiation balance. And its fundamentals are fairly simple, but really interesting and unique, of that the sun's energy comes in as very high energy. The sun is very, very hot, so its energy comes at what we call short wavelengths. That passes through the atmosphere unimpeded. When it strikes the Earth's surface, it can a couple things can happen to it. If you have lots of sea ice and it's white, or you paint your roof like I just did this last weekend white, I don't know why I did it in June. I participated in a climate experiment on my roof. Did not go well. Painting things white or having ice or snow reflects that shortwave radiation back to space. Nothing happens to it. Okay, it just goes back to space. If it's at all absorbed by dark surfaces, which a lot of it is, that energy is basically slowed down, converted to long-wave energy or thermal energy. That thermal energy tries to go back out to space. We have these little things called greenhouse gas molecules, in particular carbon dioxide, methane, and nitrous oxide are the big ones. Water vapor is also one. That based on the shape of the molecules, they get excited by this energy and start to oscillate, and they give off a part of that energy. They give it off in every direction because they're molecules, but they give off some of it back down to the planet. And so that additional downward reflection, or it's actually really absorption and re-emission of energy back to the surface, gives us a little bit of extra energy to have to deal with, right? It's a good thing, right? Because it keeps the planet warmer than it would be at its position in its orbit. But you can then tweak the amount of that energy coming back down by changing the concentrations of these particular molecules. Okay, so again, it's not an argument of getting rid of the greenhouse effect. Nobody's arguing for the abolishment of the greenhouse effect. We're not talking about getting rid of our atmosphere. It's really about this idea of what's the impact on change of these. Again, it's a little counterintuitive because there are not very many of these molecules. They're trace gases in the atmosphere, but they're so good at absorbing and re-emitting energy that they have an impact on the radiation balance. So we look over the last 1,000 years of temperature changes. Again, lots of variability on the planet. It's a very dynamic system. CO2 emissions are fairly flat. We look at the last 150 years from basically since the 1800s to present. You get real marked changes in CO2 concentrations, changes in carbon emissions, and then temperature changes as well. And again, if this was all I was going to present to you, this is weak, right? Correlation is not causation. I can't just put up a bunch of graphs. I think I make this joke, but if you plot the number of pirates, you get a perfectly inverse relationship over time. There were a lot more pirates in the past, there are less now, so they could be equivalently driving global warming as well. That's not true. That's spurious correlation, right? Okay, so this again is not about this one thread of evidence. It's about many threads, and I'll try to weave into today. So we know from the previous slide